Have you ever looked at a new field and wish there was just a direct path? You know, a way to really understand what matters, like cutting through all the noise and getting straight to the stuff that makes a difference. Well, today we are doing exactly that. We're taking a deep dive into the core programming tools, the ones that truly empower a Red Hat Certified System Administrator, an RHCSA. And this isn't just about knowing which buttons to push, right? It's about mastering a really crucial skill set for managing Linux systems, managing them efficiently, securely. Our source material today, it's a pretty comprehensive guide for anyone looking to really get a handle on this. Think of it as a shortcut to becoming a pro.
Yeah, and what's fascinating here, I think, is how these tools change the game. They don't just help you patch things up when they break. They really transform you from someone just reacting, a troubleshooter, into someone proactive, someone who architects reliable systems. It's much more about building and maintaining, not just fixing problems after they happen. I mean, mastering these programming tools, it gives you the foundation to actually customize how systems behave, automate tasks, even build software from the ground up in GNU Linux.
That context is fantastic. It really paints the picture, doesn't it? The difference between just using Linux and, well, truly mastering the environment. Okay, so let's unpack this. When we talk about these essential programming tools in GNU Linux, where do we even begin? What's the absolute bedrock here?
We absolutely have to start with bash shell scripting. That's the fundamental skill, hands down. Because the bash shell, it's doing double duty, it's your command line interface, and it's this incredibly powerful scripting environment, which means you can automate all sorts of repetitive stuff. Think about like saving hours on daily backups, or monitoring system health smartly, or maybe even onboarding new users automatically.
Right, taking those tedious tasks off your plate.
Exactly. And for scripting itself, you need to get your head around the core elements. Variables, obviously, conditional statements like if, else, so your scripts can make decisions, loops for repeating actions, functions to keep your code organized and reusable, and command substitution, that's where you use the output of one command as input for another. Super useful. And you'll often be combining bash with these really essential text processing tools, like sended.
So said the stream editor.
Yeah, think of it like a super-powered find and replace for entire files or data streams. Then there's awk, which is amazing for pattern scanning and processing. It's almost like a mini programming language just for handling structured text. Great for digging through logs. And of course, you've got grep for searching text quickly, cut for slicing out specific columns of data, and sort for, sorting things. Put them together, and you can manipulate pretty much any plain text output with incredible precision.
That depth on bash is fantastic. And you mentioned combining utilities. Can you give us maybe a quick real-world example? Like how might a bash script use grep and maybe zargs together to simplify something that would otherwise be, I don't know, really tedious?
Oh, absolutely. That's a great point. Grep is brilliant for finding things, but piping its output to zargs to do something with those findings, that's where the magic happens. Imagine you need to find every single log file across your system that mentions, say, authentication failure, and then you need to immediately zip up only those specific files to analyze later. Instead of manually finding each one, copying it, then zipping, a single bash command could do it. Something like grep-l authentication failure, varlog zargs tar-czvf authfailures.tar.gz. That one line finds the files and archives them. Boom, that really shows the power of these tools as building blocks, turning a manual chore into a lightning-fast automated task.
That's a perfect illustration. Okay, so bash is our scripting bedrock. It gives us the logic for automation.
Yeah.
The next logical question then is, how do we efficiently write those scripts and configure all the system files we need to manage? It's like having a brilliant plan, but you need the right tools to actually, execute it quickly and cleanly. Which brings us to text editors, I assume.
Exactly. And when you talk text editors on Linux, Vi, or usually its improved version Vim, is the most fundamental. It's almost always there, even on the most stripped down systems, which makes it incredibly reliable if you're in a tight spot. Now, I know a lot of people find Vim intimidating at first.
Guilty.
Yeah, many are. But the real insight isn't just about editing files, it's the efficiency. Once you get it, you realize your fingers barely have to leave the home row keys. It allows this almost thought-to-text flow that's hard to beat, especially when you're, say, SSH'd into a remote server with maybe a laggy connection, trying to quickly patch a critical config file. Vim shines there. You really need to master its different modes. Normal mode for navigation and commands, insert mode for typing, and visual mode for selecting blocks of text. The efficiency comes from being able to delete a whole paragraph, or copy 5 specific lines, or replace a word across multiple lines with just a few keystrokes, no mouse needed.
Okay, so Vim is the heavyweight champion.
Yeah.
But there are others, right?
Oh, definitely. While Vivim is essential, you should also know Nano. It's much simpler, very user-friendly, great for quick edits, especially if you're starting out. And then at the other end of the spectrum, you have Emacs. Emacs is incredibly powerful, highly extensible. It has advanced features like macros, scripting support. Some people practically live inside Emacs, but it does have a notoriously steep learning curve.
You mentioned that steep curve for Emacs. So for an RHCSA who's already comfortable with Vim, is there a really compelling reason they should bother diving into Emacs? Or is it more just personal preference at that stage?
That's a really good question. Honestly, for most RHCSA tasks, it often comes down to personal preference or maybe the specific team or project you land on. Vim's ubiquity, its speed in the terminal, that often wins out for system administration work. However, the big draw for Emacs users is usually its sheer extensibility. It's less an editor and more like an entire list-based operating environment within an editor. So if you find yourself needing like a super integrated environment with project management, mail clients, maybe even web browsing inside your editor, then Emacs might be worth exploring. But for the core day-to-day RHCSA stuff, Vim probably gives you 90% of what you need with, frankly, less initial overhead to get proficient. But across all these editors, the crucial skill is mastering basic file operations. Creating files, editing configs, making backups before you change things, very important, and safely opening files as root using sudo. Getting good at that means you can respond quickly and configure things effectively.
Okay, that makes sense. Moving beyond the shell and our trusty text editors, Ken, what other languages should an RHCSA maybe have in their toolkit for when scripts get more complex or need deeper system interaction?
Yeah, good question. An RHCSA should definitely have at least a working knowledge of some higher level scripting languages.
Sure.
Python is probably the big one right now. Its popularity has just exploded, mainly due to its simplicity and readability. It's very widely used for writing more complex sysadmin tools, and it has fantastic libraries for things like file operations, networking, system monitoring, you name it. Plus, a lot of modern configuration management tools, cloud automation stuff. They're often built on Python, so knowing it is really valuable for staying current.
Right, it pops up everywhere now.
Yeah, it really does. Then there's Perl. You don't see as much new development in Perl, perhaps, but it's incredibly strong in text processing and regular expressions. And you will absolutely run into legacy systems and scripts written in Perl, so being able to read and modify it is important. Ruby also gets used sometimes, particularly if you're working with configuration management tools like Chef. But overall, the key thing isn't necessarily deep mastery of all of them, but being comfortable enough to write, modify, and debug scripts in these languages, and understanding the details, like the shebang line, #.us or bunenv python, for example, at the start of a script, setting the right file permissions, managing environment variables. Those little things can absolutely trip you up if you're not careful.
Ah, the infamous permissions error. Yeah, been there.
Yeah.
Okay, so this is where things get really interesting, especially for team environments, right? Once you start writing all these amazing automation scripts, these custom configurations, a whole new challenge pops up. How do you manage all the changes? How do you roll back if something goes wrong? And crucially, how do you work with other admins without constantly overwriting each other's work?
Absolutely. And the answer, overwhelmingly, is Git. Git is a distributed version control system, and it becomes completely indispensable once you're doing any serious scripting or configuration management. Its core job is simple. Track every single change you make to your files. It lets you collaborate smoothly with others, and it keeps a complete history. So if a change breaks something, you can easily roll back to a previous working version. It's a lifesaver.
So what are the key Git things an RHCSA needs to know?
Well, the essentials are initializing a repository, git init to start tracking a project. Then git add to stage the changes you want to save. And git commit with clear descriptive messages, please, to actually record those changes into the history. Git log is vital for reviewing that history. Then there's branching. This is a really critical concept. It lets you work on new features or test out changes without messing up your main stable code, often called the main or master branch. So you'll need to know how to create branches. Git branch new feature, switch between them, git checkout new feature, merge changes back in, git merge, and delete branches when you're done. And importantly, how to handle merge conflicts. Because when different people change the same part of a file, well, Git needs your help to figure out the correct version. Trust me, it will happen in team setting.
Oh, I bet. Resolving conflicts sounds fun.
Yeah. Huh. It's a skill you learn. And when you're working with others or just want an offsite backup, you'll use remote repositories. So commands like git clone to get a copy of a remote repo, git fetch to see what's changed remotely, git pull to bring those changes into your local copy, and git push to share your own changes back. For troubleshooting day-to-day, git diff is amazing for seeing exactly what's changed between versions, and learning how to revert changes and how to use .gitignore files to tell Git which files not to track, like temporary files or compiled binaries, is also key. Studies have shown teams using version control like git report significantly fewer deployment errors. It's not just about managing code, it's really about managing risk.
That's a really compelling statistic. Makes total sense. So Git is the lifesaver for managing your own code and configurations. But what about all the other software on the system, the applications, libraries, utilities you didn't write yourself? How do you reliably get those onto the system and keep them updated without, a massive headache?
Right, that's where package management tools come into play. And for Red Hat systems, that primarily means RPM, YUM, and nowadays DNF.
Oh.
So RPM, the Red Hat package manager, is the underlying system. It handles individual .rpm package files, installing them, removing them, verifying them. As an admin, you need skills like querying installed packages, checking versions, seeing what files they installed and where, checking dependencies, verifying digital signatures to ensure they haven't been tampered with.
So RPM is the foundation. What about YUM and DNF?
Exactly. YM, the Yellow Dog updater modified, was built on top of RPM to make life easier. Its big advantage was automatically figuring out and installing dependencies. If program A needs library B, YUM would grab both. It also managed packages from online repositories, making updates much simpler. And it could handle group installations, like installing a whole web server stack at once. DNF, or Dandified YM, is the successor to YM in modern Red Hat Enterprise Linux and Fedora. DNF keeps the good parts of YM but adds significant improvements. Better performance, smarter dependency resolution, which avoids a lot of the old dependency hell problems. It also has features like modular content management and, crucially, automatic rollback capabilities. If an update fails or causes problems, DNF can often roll back the transaction automatically.
Wow, that rollback feature sounds incredibly useful.
It really is. Makes updates much safer, especially in critical environments. Beyond just using DNF install or DNF update, you also need to know how to configure software repositories, maybe adding third-party ones, managing their GPG keys for security, and things like cleaning package caches, troubleshooting dependency conflicts when they still occasionally happen. And sometimes, maybe for an offline system or a custom package, you'll still need to know how to install an RPM file manually using the RPM command itself.
Okay, DNF sounds like a massive improvement over YUM, especially the automatic rollback and the modularity you mentioned. Is there like a specific scenario or a feature in DNF that, in your experience, has genuinely saved an admin a ton of time or prevented a major headache that YUM just couldn't handle as well?
Oh, absolutely. The modular content management in DNF is a real game changer, I think. Imagine you've got an application that absolutely needs a specific older version of, say, Python or Node.js to run correctly. But the system's default version is much newer. With YMM, trying to juggle multiple versions like that was often a nightmare. You'd run into conflicts, libraries wouldn't match. Classic dependency hell. DNF's modules allow you to explicitly enable a specific stream for certain software, like DNF module enable Node.js .13. This installs that version and its dependencies in a way that doesn't usually conflict with the base system or other applications using different versions. It prevents so many headaches and allows for much more flexible, stable environments, especially in production. It's honestly brilliant.
That makes perfect sense. Okay, so we've got our package managers to handle most software installation and updates. Great. But what happens when you can't just use a package manager? Maybe you need the absolute latest cutting-edge version of something or it's highly specialized software, and you have to build it yourself from, well, its raw ingredients, the source code.
Yeah, that's when you need to dive into compiling software from source. And the main tools you'll encounter here are Make, GCC, G++A, and AutoCompDef, GCC, is the GNU compiler collection. It's the standard compiler for C programs on Linux. G++ is the equivalent for C++ programs. You'll need to get familiar with some basic compiler options, things like specifying the output name for your compiled program, setting optimization levels, do you want it fast or small, enabling debugging information, which is vital if you need to troubleshoot the compiled program later, and linking libraries or specifying header file locations, basically telling the compiler how to connect your code to other software it depends on.
Okay, so GCC does the actual compiling. What about Make?
Right. Make is an automation tool specifically for building software. It reads instructions from a file, typically called a makefile. The beauty of Make is that it's smart. It figures out which parts of the source code have changed since the last build and only recompiles those parts and anything that depends on them. This saves a ton of time compared to recompiling everything every time you make a small change. So understanding the basics of reading a Makefile is pretty key. And then there's AutoConf. Often, before you even run Make, you'll run a script called configure. AutoConf is a tool that helps developers create that configure script. Its job is to check your specific system, what libraries you have installed, what features your kernel supports, things like that. It then generates a custom Makefile tailored to your environment, hopefully ensuring the software will compile and run correctly on your specific Linux setup. So the standard process you'll see over and over again for building from source is usually run.configure, then run make, and finally run sudo make install to put the compiled software in the right place.
That .configure make install sequence feels like a rite of passage for Linux users. Now, for compiling, what's a common gotcha with those configure scripts? Something that trips up even experienced admins sometimes, and maybe how they can troubleshoot it quickly.
Ah, the classic configure gotcha. It's almost always missing development libraries. The Dove and Devil, or the Dove Dev packages. See, the configure script checks for all the dependencies the program needs before it even tries to compile. This includes not just the runtime libraries, but also the header files needed for compilation. If you have, say, libpre installed, but not libring and devil, the configure script will likely fail. And often the error message can be a bit cryptic, maybe just saying, checking for concrete write struct. No.
Right. Not super helpful sometimes.
Exactly. The quickest way to troubleshoot is usually to read the output of the configure script very carefully. Scroll back up. It often actually tells you exactly which library or tool it couldn't find or which check failed. Once you identify the missing piece, like maybe png.h, you can use your package manager to figure out which package provides that file. Something like dnf provides png.h, or apt file, search png.h. It'll usually point you right to the needed .devil package. Install that, run .configure again, and fingers crossed, it works. It catches everyone sooner or later.
Good tip. Okay, so we've covered getting software on the system, even building it ourselves. But once you're managing more than just a couple of machines, doing everything manually, it just doesn't scale. It's too slow, way too prone to human error, just not feasible for complex systems. That's where automation really has to step in, right?
Absolutely. You hit a point where manual administration just isn't sustainable. Automation tools are essential for managing systems efficiently, consistently, and for reducing those inevitable human errors. Ansible is hugely popular, mainly because of its simplicity and its agentless architecture. Agentless means it typically just uses SSH to connect to the machines it manages. You don't need to pre-install special software, an agent, on every single server. Ansible uses playbooks, which are written in YAML, a fairly human-readable format, to define the desired state of your systems. Things like, ensure this package is installed, make sure this service is running, copy this configuration file.
So Ansible is agentless and uses YAML. What about the others, like Puppet and Chef?
Right. Puppet and Chef are the other big players in this space. Unlike Ansible, they typically use a client-server model. This means you have a central master server, and you install an agent on each machine you want to manage, the nodes. Puppet uses its own declarative language in files called manifests to define the system configuration. The agents periodically check in with the master and apply the configurations defined in the manifests. Chef is similar, also client-server, but it uses Ruby for its configuration language, organized into cookbooks and recipes. It tends to be a bit more procedural than Puppet's declarative approach. Understanding the trade-offs is important. Ansible is often seen as easier to get started with, great for ad hoc tasks or orchestrating complex multi-step deployments across many machines quickly. Puppet and Chef, with their agent-based models, are often favored for maintaining a consistent state over time in very large, highly standardized infrastructures. They excel at ensuring systems stay configured correctly, but they generally require more initial setup.
That agentless approach with Ansible definitely sounds appealing for getting started quickly. But you mentioned trade-offs. Are there scenarios where that client-server model, like Puppet or Chef uses, might actually be a more robust solution, even with the extra setup involved?
That's a really sharp observation. Yes, absolutely. While Ansible's simplicity and push-based nature are fantastic for many things, the continuous enforcement you get with Puppet and Chef's agent-based pull model is a significant advantage in certain contexts. Think about compliance or strict configuration management. With Puppet or Chef, the agents on your nodes are constantly checking in with the master server maybe every 30 minutes. They verify that their current configuration matches the state defined on the master. If someone manually logs in and changes a critical setting, maybe stops a required service or modifies a security configuration, the agent will detect this configuration drift on its next run and automatically correct it, reverting the change back to the desired state. This continuous monitoring and automatic remediation is incredibly powerful for maintaining consistency, security, and compliance at scale, especially in regulated environments. Ansible typically only makes changes when you explicitly run a playbook. So for those large, strictly controlled environments where ensuring systems don't deviate from the standard is paramount, the overhead of managing agents can be a very worthwhile investment. But regardless of which tool you choose, the best practices are universal. Always test your automation code thoroughly before running it on production systems. Use version control Git for your playbooks, manifests, or cookbooks, and document everything clearly.
Testing and documentation, always key. Okay, but even with the best automation, things inevitably go wrong sometimes. Scripts have bugs, programs crash, configurations conflict. So how do we fix them? What are the essential skills for actually troubleshooting scripts and programs when they misbehave on Linux?
Yeah, troubleshooting is a core skill. It leads us right into understanding how to debug. The absolute first step is always error interpretation. Really read the error messages. They often contain vital clues even if they look cryptic at first. Then learn to examine the system logs. Tools like journal.exe all on modern systems, or looking in varlog for older logs managed by logrotate. Logs are your best friend. Also, always check the exit code of a script or command. In Bash, $ holds the exit code of the last command. 0 usually means success. Anything else indicates some kind of failure. For debugging shell scripts specifically, running them with bash nash $, is invaluable. It prints each command right before it's executed, often with variables expanded. It shows you exactly what the script is actually doing line by line. If you're troubleshooting Python scripts, the built-in debugger PDB lets you step through the code, inspect variables, and figure out where things are going wrong.
What are some of the really common issues people run into?
Oh, the usual suspects. Simple syntax errors, a missing quote, a typo in a command. Incorrect variable usage, maybe forgetting to scope a variable correctly or misspelling it. Permissions problems are huge. You know, I once spent half a day tearing my hair out over a script that wasn't writing a file.
Let me guess.
Yeah. Finally realized the user running the script didn't have write permission in the target directory.
Oh.
Or forgetting chmod plus x to make a script executable in the first place. It's always the simple things, isn't it?
Always.
Other common pitfalls include incorrect environment settings, maybe a required path isn't set, or network-related problems if your script needs to connect to another service or server. But just as important as fixing errors is preventing them. Practicing defensive coding, like checking if a file exists before trying to use it, validating input, adding proper error handling within your scripts saves so much time in the long run.
It's those little permissions things that catch everyone, I swear. Okay, so beyond just fixing things when they break, there's that constant vital concern for any administrator. Security. What are the absolute core security practices an RHCSA needs to internalize and just live by?
Security is non-negotiable. It has to be baked into everything you do. Foundational principle number 1, the principle of least privilege. Always grant users, and even processes, only the absolute minimum level of access they need to do their job and no more. This means getting file permissions right, using chmod for read, write, execute, chown to set ownership, and understanding how a mask affects default permissions for new files. It also means enforcing strong password policies. For authentication, using sudo correctly is crucial. It allows specific users to run specific commands as root or another user without having to share the actual root password. Configure sudo carefully. And for remote access, absolutely insist on secure key-based SSH authentication. Disable password-based SSH logins wherever possible. It eliminates brute force password attacks.
What about monitoring and updates?
Vital. Continuous monitoring is key. Regularly review system logs using journal.pactula or checking files in varlog. Look for anomalies, failed logins, unusual activity. Set up alerts for critical events. And keeping systems up to date is perhaps the single most important security task. Diligently apply security patches and software updates using your package manager, like the NF update. Outdated software with known vulnerabilities is one of the biggest attack vectors. Don't delay patching. Network security is also critical. Configure your firewall tools like Firewalled or the older IPTPULs to block all traffic except what is explicitly needed. Understand firewall zones and rules. Disable any services you're not actually using to reduce the attack surface. And always use encrypted connections, HTTPS for web traffic, SSH for remote administration, VPNs where appropriate. And then there are additional measures like encrypting sensitive data at rest using tools like GPG or OpenDLL, and implementing two-factor authentication 2FA for user logins whenever you can. It adds a huge layer of protection.
That's a comprehensive list. Okay, final piece of the puzzle then. Let's say you're writing all these amazing scripts, these configurations, you're using Git, you're automating. How do you make sure that the code you write isn't just functional, but actually, good? Easy for other people or even your future self 6 months from now to understand, maintain, and maybe build upon.
Yes. Writing testable and maintainable code. This is what separates okay admins from really great ones, I think. It's about professionalism and long-term thinking. Clarity and consistency are paramount. Use proper indentation, please. Consistent spacing. Choose meaningful names for your variables and functions. Don't use XYZ if you can help it. Make it readable. Comments are incredibly important, but focus on the why, not just the what. The code itself shows what it does. Your comments should explain why you made a particular choice, or clarify a complex piece of logic, or warn about potential pitfalls. Think about the next person who has to read it. Modularity is key for maintainability. Break down complex scripts into smaller, reusable functions, or even separate modules or libraries if possible. This makes the code easier to understand, easier to test individual parts, and promotes code reuse. Don't write monolithic 500-line scripts if you can avoid it.
And error handling again, I assume.
Definitely. We mentioned it for troubleshooting, but it's crucial for maintainability too. Always include robust error handling. Check the exit status of commands you run. Validate any input your script receives. Never just trust it blindly. Handle potential failures gracefully. Testing is essential. Test your scripts in a controlled environment before deploying them to production. Think about edge cases. Consider writing automated tests if the script is complex or critical. This helps catch regressions later if you modify the code. And finally, it circles back. Use version control, like Git diligently for all your scripts and configuration files. Track your changes, and write clear documentation. Even a simple readme file explaining what the script does, how to install it, any configuration needed, and maybe some usage examples makes a world of difference for anyone else, or future you, who needs to use or modify your work. It really boils down to thinking beyond just, does it work right now? You need to ask, can this be easily understood, tested, and improved upon later?
Wow. Okay, we have covered a ton of ground. We've journeyed right from the command line with Bash, navigated the interesting world of text editors like Vim. We explored the power of Python, wrangled Git for version control, mastered package management with DNF, even tackled compiling from source code. Then we moved into automation with tools like Ansible, learned about troubleshooting, locked things down with security best practices, and finally talked about writing code that actually lasts. That was an incredible deep dive. I feel like if you followed along, you now have a much clearer roadmap. You're not just informed, you're actually on the path to being truly capable in G and Linux system administration.
Exactly. And if we just zoom out for a second, connect this to the bigger picture, mastering these programming tools, it doesn't just make you a more efficient administrator. That's true, but it's more than that. It really transforms you into a kind of digital craftsman, someone capable of not just maintaining the systems we rely on, but actively shaping them, improving them, building the digital infrastructure of tomorrow. So the question to leave you with is, think about your own environment, the systems you work with, or maybe want to work with. What problems could you solve now with a bit of automation? What could you make more resilient or secure? What will you build or automate or secure next now that you're armed with these insights?